We're going to continue to look at techniques using the Gershgorin discs. If you didn't see the first video, it's linked below for the introduction of Gershgorin discs. And so in the last video, we looked at the general ways of using Gershgorin discs to bound eigenvalues. Now we're going to go a step further. So let's first take a look at this matrix here, call this G. Let's find the Gershgorin disk for this matrix. I'll go through like we did before. Let's say look at row 1 or disk 1, however you want to think of this. So row 1, remember we're looking at the diagonal element, and so the center is at -7 and 8, and then we want the radius of row 1, and the radius, I took kind of a simple example here so we could calculate these pretty quickly. So there we have it. The center, of course, is the diagonal element on each row. So the center here was -7, 8, 5, 4, -8, 7. Then sum the off diagonal elements like we did in the last video, and we have this. So when we plot these on the real and imaginary axes, we get something like this. So these are the actual eigenvalues. And again, the Gershgorin set is comprised of all these disks here. In fact, you can see that this particular disk is inside the other, so you could almost ignore that one because it's already covered by this one out here. And so that's our Gershgorin set of the original matrix. Now we're going to do something different. We're going to also find the Gershgorin disks for the transpose of the matrix. You recall that the transpose of a matrix has the same eigenvalues as the original matrix. So let's take a look at that. Now let's look at the transpose of this matrix. Remember, for the transpose, we interchange rows and columns. So we're going to make this column into the first row. So we're going to put -3, 7. Then we're going to make the next column into the second row, 7, 5 plus 4i, 5. And then take the third column and turn it into the third row, and that gives us the transpose matrix. Now we're going to find the Gershgorin disks of our transpose matrix because it contains the same eigenvalues as the original matrix. Therefore, our Gershgorin set will bound the same eigenvalues as the original. So when you do that, we have the centers, and the centers are actually going to be the same because you take the transpose, the diagonal elements don't change. Now, and interesting, the first radius was exactly the same for our original Gershgorin set. Now, the second radius changed, and the third radius changed. And now, when we plot those for the transpose matrix, this is for the transpose, we get these disks. And they are slightly different than our original. So our original, for the original matrix, the Gershgorin disks look like this. And they're a little bit different. And now it's important to keep in mind, this set contains all the eigenvalues, and this set contains all the eigenvalues. So if we could intersect those two sets, we would get a smaller set that includes the eigenvalues. So let's take a look at this on MATLAB. Here I plotted the original set, the original Gershgorin set. And now I've superimposed the Gershgorin set for the transpose of the matrix. As I mentioned before, notice that one of these circles up here overlaps the original one. So it may be hard to see, but there's a dotted one underneath the main one there. In other words, right here, there's a dotted one and then superimposed with a solid one. Again, the solid ones from the original set, the dotted ones are from the transpose. We can superimpose these two sets and find a smaller set that includes the eigenvalues. Now, when we're intersecting the two sets, it could be a little bit tempting to take, this circle from the one set and maybe this circle from the other set, etc., and get a really small set. But we have to be careful that we're intersecting the two sets that we originally had. And then we have to treat those as complete sets. In other words, we're intersecting this whole set with this whole set. And let's do that. And this is what we get when we intersect those two sets. Now, again, notice that the black circles with the original set, the original Gershgorin set for the original matrix, the dotted lines are the transpose, and now these these purple dots here represent the intersection of those two sets. Notice we saved some space here. In other words, the original set had a lot of extra stuff on that left part, and that's now been eliminated by intersecting it with this transpose. And so now in this case, again, we've reduced the set a fair amount, but now sometimes, again, if the matrix is bigger, more complicated, doing the transpose can sometimes greatly reduce the inclusion set. So again, what we have here is a set that includes all the eigenvalues of the original matrix. And as I mentioned, what we've saved is kind of this area right over here. In other words, the original set included this, and we've saved that area. And as I mentioned before, it was tempting to kind of just intersect, just use the circles themselves. But, we would have missed this part here. Unfortunately, we can't exclude that part, at least not yet. Now, another thing that we can use is the fact if two matrices are similar, then they have the same eigenvalues. And recall that two matrices A and B are similar if there exists an invertible matrix P such that B equals P inverse A P, like this. So in other words, if we could find a matrix similar to our original matrix, we could find the Gershgorin disks of that matrix, and that would give us another set that would contain the eigenvalues, or we can intersect that set. Now, the simplest way to find a matrix P that'll do this is, say, something like this, is to use something of this form, this matrix, that's just a diagonal matrix with non-zero constants along the diagonal. Then, if you recall, it's easy to find the inverse of this matrix. So we can just find the inverse. Remember, if you have a diagonal matrix, and again, if these are all non-zero, the inverse of that matrix is just the reciprocal of those diagonal elements, like that. And again, you can't do this with any old matrix. It has to be a diagonal matrix, and these elements have to be non-zero. So we can use this to find a similar matrix, and then we can find the Gershgorin disk of that similar matrix, and that'll give us another set that includes the eigenvalues. So let's use this method to go ahead and find a matrix similar to our original matrix. Now, it can be kind of tricky because when you're guessing at these diagonal elements, sometimes, depending on which one you guess, sometimes it'll increase the size of one disk and then decrease the size of another. And so, you have to sort of play with this a little bit. Now, I just decided to change one of these. So I'm picking 1, 1, 1.2. And as I mentioned, the inverse of that would be 1 over 1, which is 1, 1 over 1, which is 1, and 1 over 1.2. Then I multiplied the inverse times our original matrix G, which was this matrix right here, times P, and I got this. Now what I'm going to do is find the Gershgorin set, the Gershgorin disks for this matrix. The purple represents the intersection of the Gershgorin disk for the original matrix and for the transpose of the original matrix. And again, that is a set that includes the eigenvalues. Now, I superimposed on that these blue dotted disks, and the blue dotted disks represent the Gershgorin set for that similar matrix that I created. And so notice, if we were to intersect the set represented by the blue dashes with the purple that we had before, notice we'll reduce the inclusion set somewhat. Now notice up here at the top, we don't reduce it at all, because actually the purple's inside, so the blue discs don't help us at all up here. Same thing over here, they don't help us. But notice down here, the blue discs, the set represents the Gershgorin set for the similar matrix, does not include this region down here. So we could actually eliminate this region down here. And so we would reduce the size of the set by using the Gershgorin set for the similar matrix and intersecting that. So doing the similar matrices and finding their Gershgorin sets can help us reduce our set that includes eigenvalues. Okay, we're going to do one more thing, and that's going to be, we're going to generate a whole bunch of these similar matrices, we're going to vary like these diagonal elements. Like I'm going to do like about 20 of these. I'm going to make this like 0.2, 0.2, 0.2, then maybe 0.2, 0.4, 0.4. And I'm going to sort of vary these and make about 20 similar matrices. And again, since there's matrices that are similar to our original, they're all going to contain the same eigenvalues, and we'll find the Gershgorin sets of all 20 of those and intersect those and see what we get. I'm going to do that on MATLAB. So first, let's go back and look at our original Gershgorin set was the set enclosed by these black circles. And then when we found the Gershgorin set of the transpose, we intersected with that with the original, got these, I'm a little bit colorblind, I think that's purple, these purple dots here. So the purple represents the intersection of the original Gershgorin set with the Gershgorin set of the transpose matrix. And now we're going to take about 20, you can almost consider them random similar matrices, and we're going to intersect all of those and see how small of a Gershgorin set we can get. The blue dots here represent the intersection of those 20 or so similar matrices. Again, each of those matrices contain the same eigenvalues as the original, and therefore, if we intersect all the Gershgorin sets from those matrices, we get those blue dots you see here. Notice how we've reduced our set considerably. In other words, we've got it down quite a bit. In fact, if we did more than 20, we could probably reduce it even more. Now, there's going to be some point, a point of diminishing returns as we get our set smaller and smaller. But you can see that this set is quite compact, especially compared to the original set, which was the black discs. And then we got it a little bit smaller by intersecting the Gershgorin disc from the original set and the transpose matrix, which is the purple. And then the dark blue there represents the set that we get when we intersect those 20 similar matrices. So it's quite interesting when you do the similar matrices, you can reduce the set quite a bit.